Hello everyone, welcome to part 2 of derivatives. Today we're going to be looking at graphs. Part of the intent of this is in our first lesson we did all the some analytic techniques for finding derivatives, and now we want to try to build some understanding of what a derivative is and what it means. Okay, so we're going to use some visuals to try to do that today. We're going to start here with an example that we did in the previous lesson, and we had previously found the derivative of this. Rather than go through all the steps again, I'm going to actually just pop out the derivative, and the reason we're going to do that is down here we're being prompted to find a bunch of derivative values. Notice that says f prime. That means the derivative, the slope, rate of change, those are all sort of interchangeable. Okay, so remember f prime of x from the previous lesson was 4x minus 3. And that makes it really easy to fill in the rest of these with just mental math. That's saying pop a 0 in there, 4 times 0 minus 3 is negative 3. If you plug in a 1, you get a 1. If you plug in a negative 1, you get a negative 7. And I think I'm going to plug in a 2 just for good measures. I'm going to find f prime of 2. When I do that, I get 8 minus 3. That's 5. Okay, now the reason I got these here is that's going to make it really easy to graph over here. So I'm just going to take these, I'm going to start plotting the points. 0, comma, negative 3. Okay, and I run out of axis, but it's down here somewhere. 1, comma, 1. Okay, that's not bad. What do we have? Negative 1, negative 7. Okay, that's way off of the screen, so I'm not going to graph that one right now. F of 2 is 5, so 2 and then up to 5 is about up there. And when I connect these, we can see that that's roughly and basically a line. Okay, so let's talk about what that means, okay, and what each of these means. Right here, when we see f of 0 equals negative 3, remember that's, f prime of 0. Remember, prime means that we're talking about a derivative. We're talking about a slope. And so that's saying the slope at an x value of 0 is negative 3. So I'm going to sketch that on there. Let's see if it makes sense when you see it visually. When I sketch on the tangent line at that point, first of all, does that have a negative slope? Yeah, sure it does. Second of all, does it look like it's negative 3? Yeah, maybe. Let's test another point and see if it still holds up. Okay, let's try this one. F of 1 equals 1. If I go to an x value of 1, the slope, or the rate of change of this function at that point should be 1. Let's see if that's true. Okay, go to 1. 1 is right here. Go to my function. Draw in my tangent. Does that look like a positive slope, and does it look like it's 1? Notice how this is not as steep as the negative 3 is. Okay, and that makes sense. And so what this point is saying when it's above the axis, it's saying a couple things. First of all, slope is positive. The rate of change is positive. The word we want to use for it is that it's increasing. Okay, now we're talking a little bit of calculus vocab. So say our function is increasing. And what that means is if I'm tracing along the function, moving from left to right, when I get to this point, I'm going up. The y values are increasing. Okay? And it's not saying that they're above the x-axis. It's saying wherever they are, they're headed upward. Okay? That's all we're saying here. Down here, similarly, below the axis, if up was increasing, down is decreasing. This is saying that if I'm tracing right here, I'm heading in a downward direction, and sure I am. That is the rate at which I'm going down. Okay? So that's our first derivative graph. Now, they're going to be quicker than this. We're not always going to find the derivative function, plug in a bunch of values, and plot a bunch of points. We're going to do this sort of intuitively. There's a couple tricks to it. We're going to talk about that first, so let's get to it. Okay, first thing we're going to look for when we want to graph is something called a critical point. This is a huge, huge concept in calculus and one that's really, really important to get. Okay, so critical points are defined in a couple different ways. Okay, the slope of the original graph is 0. So horizontal tangent lines. Now, in order to have a horizontal tangent line, typically one of two things has to happen. Your function has to either come down to that point, turn around and head back up. That would be a minimum value of the function, or a little valley. Or it could be coming up to its highest point and coming back down again, but it's going to have that moment where it's horizontal at the top. Okay? And that's what this is saying right here. They happen where there's a max or a min, usually, on the original function. And then make sure, if you're taking notes right now, make sure you get this in there, that it's where f prime equals 0. Because that's something we're going to use a lot in future lessons. Okay, let's look at it visually. Visually speaking, it's these maxes and mins. These sort of, some people call them turning points on the graph, where it was going down and now it's going up. In between, but between going down and going up, at some point you must have been not going anywhere at all. So those are those points. Okay, and with that in the bag, let's look at one more thing, then we're going to graph some on our own. Okay, here's another graph. This one is a derivative graph. So as you're watching the video, be careful, slow down. This can be a little bit brain twisting for a minute. Okay, this is not the regular graph. This is the derivative graph of some function. So this is f prime of x. Okay, and what we're asked is what do the critical points look like on this graph? Okay, so, or the critical points from the parent function, how do they get graphed on the derivative? So remember, it's where f prime equals 0. We wrote that down just a minute ago. Okay, and remember, this guy right here, that's not an x value, that's a y value. So it's wherever the y values on this graph are 0. And so it's right there, right there, right there, right there, right there, and right there at the zeros, or as some people have called them recently, the x-intercepts. Okay, so if you want to call them that, that's totally fine. So we find our critical points, and then we plot them as zeros. Let's try it. Okay. You may want to pause the video at this point, and you may try to sketch these out. Perhaps that would be a way that you could go through for your note-taking. So you probably can't keep up just drawing them with me. Okay, so first one, I'm going to look at it. Looks like it's linear. I'm going to ask myself first about its slope. Okay, this thing has a negative slope. Negative slope tells me it's a decreasing function, which tells me my derivative has to be only below the axis. So I'm going to go point by point. I'm looking here. It looks like everywhere I look, the slope is -2. And that means the y values on my derivative function are all at -2. And so there's my derivative. That's all it is. Yeah, that one was an easy one. They get a little more exciting. Let's go to the next one. Okay, first thing, identify the critical points. Critical points on this one, it's right here up at the top. And so when I see a critical point, what I'm then going to do is I'm going to, for my derivative function, remember that's a 0. So immediately I'm going to go down here, I'm going to put a 0 right there. That's now broken my graph up into 2 sections. And I'm going to look at them one at a time. We're cutting this into little bite-sized chunks here. Okay, left-hand side, first question, is it increasing or is it decreasing? As I move right to left to right, that thing is increasing, which means my derivative graph is above the axis. It's steepest down here, it's getting less steep, and so my derivative is going to be at its highest, getting less high, closer to 0. On the right-hand side, this function now decreases. It goes down, and it's getting steeper, 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 steeper. And so I'm going into negative land here, and I'm getting further away from the x-axis into larger absolute value of negative values. Okay, and that's our derivative graph. On this one, it's very similar. We're going to plot our critical points, so I'm going to turn those into zeros. So 0, 0, and now we have 1, 2, 3 regions of the graph. Those 2 cuts made 1, 2, 3 regions. Okay, we're going to look at them one at a time. And what that's going to look like is, here I'm increasing, so I need to be above the axis, increasing. Here, it's decreasing, and we're going to add one thing to this. When it's decreasing and then changes back to increasing, I want you to find the steepest point. Now, this is actually what's called an inflection point. We're going to talk more about that a little bit later, in a later lesson. But for now, think of it as the steepest point. So it's 0 here, 0 there. It gets steeper, steeper, steeper. My steepest point is there. Now, steepest means it is the biggest slope, or the biggest absolute value of the slope, which means our derivative is going to have its biggest, or its least, its lowest y value. And so I'm going to take that inflection point and drag it down as far as I can. Now y'all, I just plotted that at -3, and I have no idea what the slope is right there. And so what I'm looking for when I grade these, I'm not looking for the exact values. I'm looking for you to demonstrate that you know it's steepest right there, and so that's as far down as it goes. And you do connect the dots here. Make it a curve. Especially in our next lesson, we're going to talk about why that has to be curved. We're going to see it algebraically. For now, sort of take my word for it, at least for a minute. Okay, and then out here in our final region to the right, it's increasing, it's going up, 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 so I am also going to be above the x-axis. Okay, there's that one, and we'll do one more. Let's take this one, critical points. I want my steepest point, so it is increasing, increasing, increasing. That looks like the steepest point to my eyes. If yours looks a little different, that's okay. You can alter it so it fits yours. Just looking for understanding that you see where the steepest point is. I mean, it's got to be reasonable, but it doesn't have to be perfect. Okay, on the left, looks like we are decreasing. Okay, so decreasing. Right here, we are increasing with the steepest point. Excellent. And then out here, we are decreasing again. Okay, and so there's something I'd like you to notice right here about these functions. In this first function, the original graph was something like -2x, and the derivative graph was -2. This thing right here, it's a parabola. I don't know too much about it, but I know it opens down. It's some sort of -x² type of deal. And then our derivative was linear with a negative slope. It's some sort of a -x. Down here, our original function is some sort of cubic. And our derivative is some sort of quadratic. And the same thing here. This is, I mean, I don't know that it is, but it looks an awful lot like a cubic. And this looks an awful lot like, or as a negative cubic, this, and the derivative looks an awful lot like a negative quadratic. So what's the pattern? Every time we take a derivative, look at this. 2 down to 1, 3 down to 2, 3 down to 2, 1 down to no power. We lose 1 on the degree. And so that's one of the reasons why, like on this example, I wanted you to curve this like a parabola, because later we're going to see that that's what happens. If it's something cubic, it's going to turn into something parabolic. Okay, that's going to be a pattern that we're going to have. Okay, we're going to do a couple more of these. There they are. Okay, you may wish to pause the video and try them on your own. If not, if you want to watch, then just follow right along, okay? On this one, critical point, negative slope, positive slope at the steepest point, and then it gets a little funny right here, because it's negative, but it looks like it's steepest here and it's flattening out. So I need to bring down my steepest point here, and I'm going to come back up. To my eyes, it doesn't look like this levels out all the way. That's why I'm not getting all the way back to the axis. Okay, over here, we've got a critical point, we've got a critical point, we've got a steepest point, and here we go. There it is. Okay, these two get a little tricky, but that's part of the fun, right? So I've got a critical point right here. It looks like I've got a critical point right here. Break it up into those 3 regions. Now I've got increasing. It's not very steep, but it is increasing right here. And then it looks like it's decreasing with the steepest point right there. And then it's increasing, steepest point somewhere in here, and then it sort of levels out. But it doesn't get flat, so I'm not going back to the axis. And then our last one, this one's a little funny. This one's open to interpretation right there along the axis. I know that it's not steep at all, and so I'm just going to kind of make my whole derivative right around 0 right there. I've got a critical point here, and let's graph it. This is decreasing, so we're below the axis. This is decreasing again with the steepest point here, so we're below the axis still, and then finally this function starts to increase, and so we're going up. Okay, a couple more and we'll be done. Okay, we do want to sketch this one. This one can be a little bit challenging for people who are just learning it. Do you remember what an absolute value looks like? Looks like a v. Let's sketch it. Let's look at its derivative just for practice. Okay, so I'll do my original function, f of x, in blue, and then we'll do the derivative in red. Okay, and so we're going to look for the critical points, and is that a critical point? Okay, not exactly. Okay, and the reason why it's not, remember we said that it's when f prime equals 0? Well, what's the slope here at that point? Is it 0? Maybe. Is it negative? Maybe. I still only touched it once. It's still a tangent line. Is it positive? Maybe. So, think back to what a derivative is. Remember, derivative comes from the difference quotient. The difference quotient is a limit, and if we're getting 3 different answers for our limit, what does that mean? The limit does not exist. And so if it doesn't exist, we can't say that it's 0 because it doesn't exist. So that's out. Okay? And so I don't actually know what the slope is or the rate of change at that point. All I can say is, I don't know. But if I look over here, I know that has a slope of -1. So if I come down here and plot -1, I know that all of those slope values are the same. It's not curved, slope isn't changing, and I know that goes forever. Right here, what's the slope? I don't know, so I gotta leave an open circle. I can't say that it goes all the way there. Same thing over here. Okay, this one now, so just do a positive slope, and it's 1. So I'm up at 1, positive slope. And what's the slope at 0? I can't say, so I have to leave an open circle. Okay, this is a weird case where we have a continuous function, and its derivative has a discontinuity on it. Okay, it's kind of unusual. But these are things that can come up. This little guy right here, just so you know, that's called a cusp. Okay, it's a point where we have sort of a wobbly tangent. Imagine if you had a little mountain and you set a board on it. That board could be sitting like this, but it could wobble to the side, it could wobble back the other way, it could fall off. Okay, it's not clear what direction you're going at that peak. And so we call that a cusp, and cusps, when you take a derivative, they generate a discontinuity. Okay, a couple last little things. Okay, let's talk about this. This is a fun one to think about. We are approaching Thanksgiving. I'm thinking about it already. Thanksgiving is my personal favorite holiday, and it's all about the food. And so, of course, why would we not do a turkey question? Okay, so you place the turkey in the oven. Turkey is cold. It's been in the fridge. Hopefully you thawed it out first, and hopefully you didn't put a frozen turkey in the fryer, because that could burn your house down, so don't do that. But you're placing a cold turkey in the oven, and what's it going to do? Well, is going to heat up, right? And so how does it heat up? It heats up by some function. We've got our temperature here. That's the temperature as a function of time. And so what we want to know is what is f prime. Okay? So remember, that's a derivative. Derivatives are slopes. The slope of a turkey, okay, that's not very helpful. I don't really care about the slope of a turkey. In fact, I don't even know what that would mean if I did care. But remember, it's also a rate of change. So what is the quantity in question? We're talking about temperature, and the rate of change of the temperature, well, wait a minute, you just put it in the oven, they ask for the sign, positive or negative. Is the temperature increasing in the oven, or is it decreasing in the oven? Well, it depends on your oven. If it's decreasing, then you need a new oven. It should be increasing. Okay, so what's the sign of that? Positive, because the turkey's warming up. It's getting warmer. Okay, what does f prime of 20 mean? Okay, well, f prime was the rate at which the temperature is changing. So this is the rate of change, rate of change of temp. And then what's the 20? Okay, we were told T is time in minutes, so it's the rate of change of temperature after 20 minutes. And it's that instantaneous rate of change. Okay, and let's get more specific on it. What if that was 2? If f prime of 20 was 2, what would that mean? Well, that means that you are adding 2 degrees per minute at that point. It's pretty good. Your turkey goes in, maybe it's 40 degrees. Especially in the beginning, it's going to heat up really, really quickly. And then what are the units of f prime? Well, let's look in here again. Okay, we've got temperature and we've got time in minutes. So based on the fact that we're filming this in the United States, we're going to use Fahrenheit instead of Celsius. Sorry about that. For us, the units at the rate it's changing, that's going to be in degrees. Degrees Fahrenheit per minute. Okay, and so that's an interpretation of a derivative and what it means to us. Okay, we've talked about maximum values, minimum values so far. I'd like you to know that those are called extrema. So it's the plural form of extreme, the extreme meaning the highest, meaning the lowest. There's a couple differences. Local, you can have a local minimum. That means in this little area, that's the lowest y value. Local maximum, in this little area, that is the highest y value. But it's not the global. Global means everywhere. So you take the whole entire graph, the whole entire function, what's the highest point? On this one, no arrows on the end. So this is the very, very highest point. It's higher than that local max. So this is the highest on the whole graph. That's the global max. Down here, this is the lowest point on the whole graph, lower than that local min. And so that is our global minimum value. Okay? So this also will allow us to find the intervals over which our function is increasing and decreasing. So, how does a derivative tell us that? What we look for is if it's above the axis or below the axis. Okay, and that's what this says right here. If f prime of x is greater than 0, it means the original function is increasing. If f prime of x is less than 0, it means the original function is decreasing. Okay, and so I'm looking at this. The one in red is the derivative. And so just by looking, I can see right here, that's hitting the origin. So it is, let's see, is this increasing or decreasing over here? And be careful, because I get that the derivative function is going down, but we're talking about the original function. And since this is above the axis, that's increasing. X is less than 0. Okay? In this interval right here, function is decreasing, because the derivative is below the axis, and out here it's increasing. Now, I'm not going to take the time right now to run that through a difference quotient and get the derivative and solve it, but we need to know visually that that's how we interpret that. Okay? That's all we have for today. Hope you enjoyed sketching some derivatives, and we'll see you next time.